Poincare inequalities on metric measure spaces has close connection to the space having lots of rectifiable curves. Roughly speaking, it says that given 2 points x and y in your space, you have lots of rectifiable curves, each with length comparable to the distance of xy, and these thetas are from some parameterizing set, and the trace, the union of their images, picks up some volume, and that volume is comparable to the measure of what would be a ball centered at x with radius dxy, and or some multiple of that. To illustrate this point, of course, the precise statements will come later. We're focusing on examples. So this simple example of two triangles meeting at one vertex as a subset of R2, so equipped with the Euclidean distance. This distance is still just what would be the 2 points, distance of the 2 points as seen in R2, and the measure is just restriction of L2. So this is a metric measure space, and we will see that this does not support a 1p Poincare inequality if p is strictly less than 2. Which is much worse than a 1-1 Poincare, which does hold for better subsets of R2. So let's see why this happens. The reason is this pinching that is happening here, and here we have very small volume, and that will be the point. So how will we construct a function violating this? So you put a function that is mostly just 1 on the top rectangle and mostly 0 on the lower rectangle, and you put all the weight of increase because, well, if you have a reasonable function with a reasonable notion of derivative, for example, Lipschitz function here with the local Lipschitz constant, or later we'll see upper gradients, whatever notion of derivative you have, you want to put the whole weight of gradient on here. And on these parts, you want to have gradient or derivative 0, which is reasonable because your function is, 0 is constant. And now the point will be that u minus u average integrated over b d mu. Well, this will be something, some constant, so comparable to 1. But then you ask, is this less than some constant which doesn't depend on the size of the balls you pick, diameter of b? So here I'm taking a ball that looks like this. It's kind of a large ball. And then I will have g to power p d mu over that ball, or maybe enlarged ball, to the power 1 over p. So does such an inequality hold, which will be the 1p Poincare inequality? But let's see. So how much should this, let's talk about Lipschitz u. Then if I take this gap to be 2 epsilon large, epsilon top, epsilon bottom, then I can afford to increase from 0 to 1 by a Lipschitz constant of u, which is proportional or even just exactly equal to 1 over epsilon. So it would be 1 over 2 epsilon technically here, but again, I'm just talking about rough numbers. So with such value of gradient, you can increase from 0 to 1. And this would serve, of course, g is 0 elsewhere. This pair would form a function plus its derivative. Now let's compute this side again. This you can convince yourself that is such. But what is gradient of g to the power p? And let's say I put all of my space. I'm being generous and not just enlarging the ball, but completely blowing it up. So 1 over p. This would be, well, the function is mostly 0 except for this blue intermediate smaller part, And that one, how much volume does it have? So it's a ball of, it's inside the ball of radius epsilon in R2, so it would be epsilon squared, comparable, so pi epsilon squared technically, times, what is value of G there? So the value of G there is on average, not on average actually, it's constant, so 1 over epsilon squared. Okay, sorry, 1 over epsilon, and then we're taking P integral. So that will be just integral of G to power P, and then you want to take power of 1 over P, which you will see doesn't matter here. So this will be epsilon to power 2 minus P. Actually, I like to have it like this, epsilon to power P, and that numbers will be to power 1 over P. Now, can we have this inequality independent of the epsilon I take? So this side doesn't depend on epsilon, and if we wanted to have such an inequality, we cannot afford to have P less than 2. So if P is less than 2, then by letting epsilon go to 0, we violate a 1p Poincare inequality. One side is a fixed value constant. Actually, it becomes even nicer. It becomes exactly equal to 1, because for most of your space, then it's exactly 1 upstairs and 0 downstairs. This quantity, this integral, becomes, if you take a symmetric ball, exactly equal to, you also take average, equal to 1/2. Okay, but when P is bigger than 2, you don't run into this issue. We don't want to prove this, so we prove that there is no better than 2 Poincare inequality. So this space X with this distance and measure does in fact support a 1p Poincare if and only if P is strictly bigger than 2. So for strictly less than 2, we said it's not possible. For bigger than 2, it does support. P equal 2 is covered by self-improving property of Poincare, that if you have some Poincare inequality for under some conditions which is satisfied by this space, you would have a little better. So if you had exactly 1, 2 Poincare, you would have 1, 2 minus epsilon Poincare for some epsilon, but that is not the case here. So also P equal 2 goes with this side. So that's kind of a very easy example to illustrate this, again, idea that spaces that support Poincare inequality must have good supply of rectifiable curve and also avoid such extreme pinchings. I will, in follow-up videos, go into a bit more complicated examples based on this basic construction. So one way would be to add more pinchings. Another way would be to add more connections. And in each case, we will see that the Poincare improves or worsens as expected. So any questions, put them in the comment. And let's go through many examples. That's my goal, so that when we present the theory, it all begins to make sense.